Hi, my name is Shahnawaz. We are going to begin this lecture with this definition, that is the definition of a constant path. A constant path is, so suppose we have a path f from the interval I to x. So I is the unit interval 0 1. So when we plug in values from I to f, if f stays at a single point all the time, then f is said to be a constant path. So a constant path let us denote this constant path which stays all the time, say at x naught by cx naught. A constant path c of x naught, c sub x naught, is a path defined as is a path given as c sub x naught of s is x naught for all s in the interval I. So this path stays at x naught all the time as s varies over I. This implies that each point in the space x can be identified as a constant path. Now let us do the following proposition. So consider a path say f in space x with endpoint is say x naught and x1, then we have first items f product with the constant path c sub x1 is homotopic to f, and the constant path c sub x naught product with f is homotopic to f. Second item is f product with its inverse is homotopic to the constant path cx, and f inverse product with f is homotopic to the constant path c. Suppose this is c x naught and this is c sub x1. Let us prove this. First we have the item 1. Now to prove that f product with c of x1 is homotopic to f, we have to cook up a homotopy, say h, which takes f dot cx1 all the way from bottom to the top to this little f. So what this homotopy is going to look like, so we have the interval I cross I, so this is the interval I cross I, and this is the space x, and let us suppose this is the path f, this is the point x0 and this is the point x1. This is the point x1 here. Now we have to take this product path to f. So this bottom is mapped to the product path, so this is reserved for f and this other half is reserved for cx0, sorry, cx1. We have to take this path all the way to f. Now at time t, suppose this is s direction, this is t direction. So at time t naught, so this whole path it is mapped to this. So this is point x0 here, x1 here, that is same as cx1. So what happens at time t is equal to 0? So at time t is equal to 0, this homotopy travels f in the half interval. So in the half interval, this is 0, this is 1. In the half interval, h travels little f from x0 to x1. This is x0, this is x1, and in the next half interval it stays at x1 all the time. So if t is equal to t0, it is h travels f in this interval, and in this remaining interval it stays at x1 all the time. So this blue region, so this is the region where h travels this little f, and this red region, this is the region in which h stays all the time at x1. So we have to cook up this homotopy. Now one can note that this blue region is bounded by the lines t is equal to 0. So this is bounded by the region t is equal to 0, and line t is equal to 1, and the line joining the point is half 0 and 1 1. Now the line joining the pointers, these two points, is the line t is equal to 2s minus 1. So this is the line joining the pointers 1 by 2 0 and 1 by 1, or this is same as s is equal to t plus 1 over 2 or 1 plus t over 2. So in this region h travels this little f. So let us define this f. Define h from I cross I to x as, so h of st. So in this interval, I mean from 0 to 1 plus t over 2, it travels f, that is in the interval 0 less or equal to s less or equal to t plus 1 over 2. So when we normalize this interval, when we scale this interval, f takes the argument 2s over t plus 1. and in the remaining interval f stays at x0, sorry, x1. So in the remaining interval h stays at x1, which is same as x1 in the other half. So t plus 1 is less than s is less or equal to 1. So one can note that f is continuous. Indeed, h is continuous. Also, h of s0, which is f of 2s, where s is in this interval. So this is equal to h of s0 is equal to f of 2s, where s belongs to the interval. So when t is 0, this is half, so s belongs to the interval 0 and half, and it is the constant path in the remaining interval. So at time t is equal to 0, h travels f in this half interval at the twice speed. So it is f, and in the remaining interval it travels this constant path. So this is cx1, and at time t is equal to 1, when t is equal to 1, h travels only f, because when t is equal to 1, this interval becomes 0 to 1, so there is no time for the constant path. So at time t is equal to 0, it is just f. So this implies that hence f is f dot cx1 is homotopic to f. Similarly, one can prove that c sub x naught dot f is homotopic to f, and it is left as an assignment for the viewer to exhibit this homotopy. Now what this homotopy does, let us know this homotopy by h. Again we have the domain I cross I. Now h travels when t is equal to 0, h stays at the constant path, h stays at x naught all the time, and in the remaining half it travels whole f. So this is the f, and this is x naught here, x naught. So this is going to look like this. So in this interval, in this region, h travels f, and in this region h stays all the time at x naught. So it is left as a home assignment for the viewer to exhibit this homotopy. Now we have the second item. We had to prove f product with its inverse is homotopic to cx naught, and f inverse product with f is homotopic to cx1. To prove f product with f bar is cx1 define a map h from I cross I to the space x as. Now to exhibit this homotopy, let us see what h does at the first place. So this is so this is our path. So this is the path f, and these are the pointers x0 and x1. So at t is equal to 0, so this is the direction t, and this is s direction. So what this actually means, f product with f inverse, is this is x, so this is homotopic, not equal to. What does this mean actually? So this means that going from x0 to x1 in the interval is same as to stay all the time at this x1. So when t is equal to 0, that means we are getting values from this line segment. So this h travels f in the half time, so h travels f in the half time, and the next half interval it comes back to x0. So that means this is f bar f dot f inverse. So this means first traveling f and then traveling back via f inverse is same as to stay all the time at x0. Now at t, suppose t is equal to t0, at time t0, so this is over cx0. So the resultant is cx0. So at t is equal to t0, what it actually does, in this time it stays at x0, then in this region, in this time it travels little f, then this time it again travels f inverse, and in the rest time it stays again at x0. So there are 4 regions actually. This is, let us make this so these 2 regions are the regions where h stays at x0, and this region, in this region it travels f, and in this region it travels f inverse. So in this first red region, which is bounded by the lines, so this is the line t is equal to 0, and this is the line joining the pointers 0 0 and half 0 half 1. So this is in this so the equation of the line joining these 2 points is simply t is equal to 2s, or s is equal to t by 2. So in this region f stays at x naught. So this is same as cx naught, which is x naught. So this is h of st. So in this region, so this is the region, this is the time when values of s are bounded by 0 and t by 2. So in this region, in this time, h stays at x naught. Now next it travels f. So that is the region bounded by this line and this line. So this is the line, so this is the region t by 2 is less than x is less or equal to 1 by 2. So in this region it travels f. So the argument is 2s minus t. So this argument comes when we normalize this interval here. So this is t by 2. Then in this region, which is bounded by the line t is equal to 1 by 2, and the line joining the pointers. Now this region is bounded by the lines t is equal to 0 and the line joining the pointers 1 0 and 1 by 2 1. So this is the line which is t minus 0 is equal to slope times, that is 1 minus 1 by 0 minus 1 minus 0 is 1, divide 1 by 2 minus 1, that is minus half, x minus x1, that is s minus 1 by 2. So on simplifying this, we get s is equal to 2 minus t over 2. So in this region, when the values of t are between half and t minus 2 over 2, so this is t minus 2 over 2. In this region, h travels f inverse, and the argument here is f of 2s minus t. Now f bar of 2s minus t is same as f of 1 minus 2s minus t by definition of the inverse. So this is plus here. And finally, in the next half region, it again stays at x naught. So this is again x naught, which is c of x naught in the remaining half interval. So it is 2 minus t over 2 less than x less or equal to 1. Now note that this, for this homotopy, note that h is continuous. H is continuous, and h of s and 0. So when t is 0, we get so t is 0, that means this is nothing here, so we get only this region here and this region here. This is just a point here, because when t is 0, that means at s is equal to 0, h of st is x naught. That is it. So we get f of 2s, where s is in the interval 0 and half, and we get f inverse of 2s, f inverse of 2s, which is same as f of 1 minus 2s, which is same as 1 minus 2s otherwise. So which is same as f dot f inverse. And similarly h of s1, when we give t is equal to 1, so these two things, they are just pointers, values at points, so we get these two things over here, because when t is equal to half, when t is equal to 1, this is 1 by 2 less than x less or equal to 1 by 2, and this is 1 by 2 less than s less or equal to 1 by 2. So these are 2 points, and at these 2 points we just get the value x naught. So h of s1 is just x naught, which is c of x naught. So this proves that f dot f bar is homotopic to c of x naught. Now again, it is an assignment, home assignment for the viewers, to prove that f product of f inverse with f is homotopic to cx1. Again, one has to exhibit such a homotopy.